So we'll take these three polynomials and try to figure out the Galois over Q. I'll leave that one. What's this? Okay, so let's look at this one first. So I'm going to rely on the formula that I gave you all last time for what the resolvent cubic was. What I get here, for this one, I got see how to factor that. Of course, you can test the roots, right, using a radical root test, but I get so notice that this has the roots of this are well, so actually you get basically this doesn't really give you anything because 4 is of course already a rational number, and then you get these two roots here. So actually what we call K, alpha, beta, gamma, that's you would join this group. So this is kind of a nice little easy quadratic extension. So in particular, now in this case, this is sort of our choice case, right? This was the one where it can split up into two things. And so what I know about the Galois group it's one of these two, depending on whether the original polynomial is irreducible over Q radical P or not. So we've got to test these things irreducibility, right? And this is actually fairly easy to do because by letting u equal x squared, and x to the fourth plus 2 plus 4, x squared plus 2 becomes u squared plus 4u plus 2. And just using the quadratic formula on this, I get two roots. Minus 4 plus or minus the square root of 8 over 2. And of course, the square root of 8 has come up earlier, right? So this is kind of, to me, it's an indication. So notice that actually this splits as u plus, well, let me write this down here. It's minus 2 plus or minus radical 2, right? So this should be u plus 2 and so what I get is x4 plus 4 x squared plus 2 is x squared So in particular, this polynomial reduces over that field, Q adjoint square root of 2. So we've got enough step to break it down. So the Galois group in this case is isomorphic to Z4. So there's kind of a nice polynomial that has a cyclic of order 4 Galois group. By the way, let me tell you in practice that if you just like make up coefficients, X4, make up some rational coefficients, the Galois group is almost always going to be S4. So these are kind of set up to work out nicely. The next one we had was X4 minus 10x squared plus 4. And so I worked out the result of cubic on this one, and I got R of X is X cubed plus 10x squared minus 16x minus 160. This is what I got when I worked it all out, and this gave me that. Oh, that's right. Now this one is an even bigger pile of silliness. So when you join the 3 roots of this, you don't get anything. Here, integral 1, and the Galois group is isomorphic to what I call B, which is Z2 for X. Okay. Any questions on that?
I'm just curious, if we actually find the roots or plot them, will we see some kind of symmetry which would also reveal these?
In some cases, and actually I'm going to give you a theorem that's kind of useful in that regard. Let's look at the last one. These ones are always. So this was the last one that we looked at. Here's what I got to resolve in cubic here. Where are I get x cubed plus 8x now in this case one of the roots is 0, so that didn't count. So basically this should be a quadratic extension because this is an irreducible polynomial Q, right? And so basically what you get is the 2 roots of this, which are, well, it's 2 radical 2i minus 2 radical 2i, but basically it's Q joined with square root minus 2, or if you like, so again, in this case, M2, so G is isomorphic to Z4 or D4. And what we have to do is we have to check the irreducibility. Let's check reducibility. Nice. I'm sorry, there should be a 4th. Now, what's the status there? Well, actually, it's fairly easy to find the roots. So here's a, maybe the quickest, most effective strategy here. If you look at x to the 4 minus 2, I can find all the roots of that fairly easy, right? It's the 4th root of 2 minus the 4th root of 2, I times the 4th root of 2 and minus of it. So if I look at x4 minus 2, this should be x minus 2 to the 1/4, x plus 2 to the 1/4, x minus I 2 to the 1/4, and x plus I. That's kind of cut down to the skeleton. Now, what I want to do is I want to try to figure out, is this thing, or is it not, reducible over this? How can I tell? Well, if it reduces, it has to reduce into two factors, both of which have all coefficients equal. Agree? Now, the first observation is it can't possibly factor into a linear and a cubic. Why?
If any of the roots belongs to.
None of the roots are in that field, right? 2 to the 1/4, not in here, right? Because in fact, this 2 to the 1/4 requires a quartic extension. And in fact, this is true of all of these. So none of the roots, none of the naked roots by themselves can be in them, right? So the only thing that you could ever do, that you could hope for, is it factors into two quadratics, right? But that doesn't happen either. Can somebody tell me why? Right. So just think about how to group these things, right? Can the product of these two be in here? Well, the constant term is 2 to the 1/2, which is not in here. This is I times 2 to the 1/2, right? Same with the product of these two here. Now, what about the product of, say, this one and this one? Oh, I think I've got it, right? Because the constant term is I times 2 to the 1/2. Well, what's the problem? Yeah, the linear term is screwed up, right? Because it's this thing plus this thing, right? And you can go through and check that no matter how you try to bundle this into a pair of quadratics, it doesn't work. So this is in fact irreducible over Q adjoined with I, right? 2. So in this case, G such the dihedral on the square. Okay, any questions on that? Okay, let me give you a theorem. Here's another one. And this theorem I think is very useful at sort of eliminating, and I'll give you a couple of examples on that. Eliminating possibilities if you know the transitive subgroups. This works, so this one starts to leave the realm of just looking at, obviously the last few I did looked at quartics and cubics. This one, you can get beyond that. So theorem 8510. Let's suppose that f of x is monic of degree n, polynomial of coefficients of z and p a positive prime. Um, but We suppose that the reduction of f of x mod p has distinct roots. F of x mod p has, n distinct roots. In some splitting field. Of x over z mod p. So when you reduce this, basically you need to have distinct roots. Then if f of x factors is a product of k polynomials, the factors is a product of those k over zp, and let's say that the degree of each of these little factors is mi, then there's an element of the Galois group over Q. Then there exists element of Galois group of F over Q of form C1, C2, CK, where each CI where C1, C2, CK are disjoint cycles. In effective length MI. So in other words, suppose you have a polynomial, right? So this polynomial has some splitting field over Q. And you want to know what the Galois group of that polynomial is, just like we did in the last problem. Reduce this mod P and check to make sure that its reduction has n distinct roots, or has all distinct roots. If that's so, factor this thing over this polynomial ring, which is kind of cool because there's only finitely many ways to do it. So ostensibly you can do this here. Read these polynomials. They have degree m1, m2, etc. There's k of them. That means that in the Galois group over Q, you had there has to be an element of k disjoint cycles of those lengths. So let's look at an example. So I'm gonna start by digging back. Let's apply this. Of course, we already know the answer to this, right? It's got to be D4, right? Let me show you how this theorem works. It helps you eliminate things, and it's very good for telling if something is alternate or whatever. this is an irreducible polynomial, degree 4 over rationals. So its Galois group has to be a transitive subgroup of S4. There are possibilities. Okay, so let's reduce this. Let's try some primes. What prime do I not want to try? What's wrong with it?
The four root of the category.
Yeah, that's right. I so want to do 2, right? Because this polynomial is very simple if I reduce the mod 2. However, if I reduce this mod 2, I get the polynomial x to the 4th, which has multiple roots. So, okay. How about this? Well, let's just do kind of a baby step here. If you reduce this mod 3, because minus 2 is the same thing as 1 mod 3. Right? Now,
That's it. Do the x plus one to the four. No, I'm sorry.
yeah, that's mod 2. So, first thing, can I reduce this? Well, I'm not sure. But here's what I do know. No linear factors. And the reason is if there was a linear factor, it would have to have a root, would it not? And clearly mod 3, 0 is not root, 1's not root, and minus 1's not root. So, okay, I'm done. Now, it could reduce this way. Or so I'm doing this by hand. But mod 3, that's the only 2 things that could happen if it factors into 2 irreducibles. And how do I know this? Well, without loss of generality, I can reduce to the case being monic. The last term has to be 1. And mod 3, the only way to get 1 is 1 times 1 or -1 times -1, because only +1 and -1 are non-zero elements. So that's convenient, right? So let's see what happens here. If I put this one back together, I get x4, a plus b, x cubed, plus ab plus 2, x squared, plus a plus b, x plus 1. I'll multiply that out. Okay. Notice that, of course, the cubic and the linear term are the same. It's good side. And for the second one, cubed, I get AB, and what do I get? -2 x squared, and I get minus a plus 1. Let's look at the second case first. This means that, well, what can I come to? What conclusion can I come to immediately?
A times b must be -1.
A plus b must be 0. And of course, that's 0, that's 0, so that's good. And what else do we have? This is 0. So here, in this case, I get A, B equals 2. Oh, let's go back here. So I get AB equals 2, and I also get A equals minus B. Do I agree with that? That do something wrong? So I get A equals 2, I get A minus B. So replacing A with minus B, hit minus B squared is 2. So what do I get? I get B squared is 1. And so, that means that B and A, well, if, for example, B is 1, then A is -1, right? And this means that, right, so I get a solution to this. Notice, well, this will work. Take B equals 1, A -1. And in this case, I get 0, 0, that's gonna be -3, which is 0. So I get this right here. So that means, what does that mean? G must contain a product of two cycles, right? This is a 2 cycle because the degree of that's 2 cycles, the degree of that's 2, right? So,
We don't have to check if those polynomial transformations.
well, if they broke down further than this would have had a root, which we've already shown doesn't happen.
Oh.
Right, so if this breaks down further, that would mean that has to have a root, so, yeah, these are both irreducible polys, have to be. Okay, any questions so far? So. So, what does that do for us?
C4, Z2, Z2. It's called Z2, Z2, no it doesn't.
No.
Just Z.
Are you sure?
The C4 has no.
Well, so for example, C4. That's in C4, right? So what can we look for that would eliminate something? Okay, so what can we find that would help something? So I want to do another example in this, but this so far doesn't show anything, and that's kind of the hazard of this, but suppose we find a prime such that And I'll let you hunt for this. There is one. Right, so you reduce it mod sometimes, 7, something. And you get, what if you get a 4 cycle?
C2, C2, right?
Then that will eliminate this. It will eliminate something else.
Does A4 also get eliminated?
No, Z4 is generated out 4 cycle.
No, I said A4.
That does work. Because the 4 cycle is odd. Right? And so if you can find a 4 cycle, and you can, then you can eliminate down to this. Now, then it takes more work. And notice, of course, that this process will never eliminate S4. Because no matter what outcome you got, there's something like that in S4, right? So that's the hazard of this. Let me show you kind of the flip side of this. See if you can find one that's got a 4 cycle. Let me show you the flip side of this. So just for fun, so I'm going to tell you a very sad story. That's going to look for a second like I'm having a stroke here. So this is an old calculus problem that I asked on an exam many years ago. You have this parabola, first quadrant. You have this line. Y is an X. And of course, just for convenience, we have to figure this out here. I think this intersects at X equals 1 minus M over A, and M comes 1 minus. I'm gonna write this way. Convenient to know what the intersection is, I guess. Everybody okay so far? So the question I asked on this is, A is fixed at some positive number, for what value of M does that line cut that area in? Right? So let's solve this. Well, so the first thing I'm gonna do is figure out what the total area is. So the total area the integral from 0 to 1 of just find the area under the curve. Parabola from 0 to 1, and this is so this is A over 6. Okay. And so to solve the problem, what you want is, and of course this is part of the calculus thing, right? You either want this area to be half of it, or you want this area to be half of it. But I think the smarter way to do it is finding the top area. Well, by the way, just Y. In this top area, there's only one interval, right? Because the top function is always the parabola, the bottom function is always a line. Whereas if you do it here, then it's the line for a while and the parabola for a while, which is obnoxious.
Oh, but it's a triangle.
Well, that's right, it's a triangle, but still there's 2 things to do, and it's just, so here's what we'll do. So A over 12, you want to be the integral from 0 to A minus M over M of the top, which is the parabola, minus the bottom. Everybody agree with that? By the way, at this point, this is where I'm happy with my kids. If they got that set up, then, that's fine. But of course, the good people always wanna go for the brass ring and get everything we can, so let's see what we, see what we want here. This is so that'll make that a little bit easier, I hope. And this is going to be a minus m over two x squared minus a over three x cubed. That look right to you guys? Yeah, it does look gross, doesn't it? But actually, a little miraculous thing happens, because when you put this in right here, you get a minus m cubed over two m squared. Right, and this is minus a times a minus m cubed over three in three m cubed. So this is well, let's see what this is going to be a minus m over m one squared. So pull that out, and that leaves me with a minus m over two. And this leaves me with a times a minus m over three. It's just in this here.
Is it over M or over A?
It is over, yeah, it's over A. That's a huge difference. Yeah, that's what's in this, exactly. I'll see, it can happen to anybody. Thank you for catching that. So this is going to be, that's why I think we're canceling out. So this is a minus m cubed over two a squared. There we go. And that's what, yeah, that's exactly what I think down here. This is a minus m cubed over two a squared. This is minus a times a minus m cubed over, there we go. And see, this calms down the powers of a, right? This cancels. And this is a minus m cubed over two a squared minus a minus m cubed over three a squared.
So you get that over six A squared.
That's right. So this is a minus m cubed over six a squared. And remember, this was supposed to be a over 12. Right? So if you work this out, you get, well, let's work it out. We get 12 a minus m cubed, multiply this, and you get 6a cubed. And so I get 2 if you root both sides. And so what are we trying to find the m, right? So a minus m is equal to a over the cube root of 2. And so I get m is equal to whatever a is times 1 minus 1 over So take whatever A is, multiply by the crazy thing. Right, okay with it? Now, what's this got to do with anything? Well, here's where the sad part of the story starts. So this was a large literature calculus class, and of course, there's all things. And so I get a list of students that want to take a makeup. And most of the students took their makeup and went, but I had this one student in class that missed the makeup and missed the makeup and makeup and blah, blah, blah. And so, whatever. So he finally shows up, and I had fixed up his test with all new problems, except for the one replacing that. Well, I can't give him something easier than everybody else had, and that was kind of my showpiece problem for that one. So I was trying to figure out what to do with this guy. So I said, I know what I'm gonna do. Same setup, but now find the value of the slope such that when you rotate this around the x-axis, this cuts it into two pieces of equal volume. Yeah, don't take the makeup. Now, of course, the same as the other group of students, if the student had just set it up right, then I would probably given all the points. However, to solve this problem, well, like I said, this person hadn't shown up several times, so I had to think of something on the fly because it was a makeup of makeup of makeup. So I threw that on there. It was late in the afternoon and I was bored and I worked through the problem, and I wonder to this day if he could hear the laughter coming from my office. Because what you can do, so we're gonna find the m such that that splits that into two pieces of equal volume. Find solution to polynomial in m over a, which is essentially what we did here, right? I mean, that was kind of you can think of this as a polynomial variable m over a. That's kind of what we did. And the polynomial that we got, by the way, and this is the polynomial I got after a lot, almost a trip to the chiropractor doing reductions. So I reduced this to, this poor student had to find roots of the polynomial. Right. And so, of course, after reducing this a bunch of times, I got this polynomial, and I was like, yeah, well, you know, the rational root test doesn't work too well on this one. Now, admittedly, there's an 8 here, but the previous theorem that we had, this is an mnemonic polynomial, but we can do this as long as we have multiple roots here and it's relatively prime to 2. So all I got to do is skip 2 and any other primes for which this is. So I reduced this model 11. Sitting all playing around, I reduced this model 11 and I got the following factorization. Six. That's right. And I got that. You can test me on this if you like, but it turns out that model 11, these are both irreducible polynomials. The good thing about a quadratic and a cubic is you can actually verify this, because if a quadratic or a cubic reduces, it has to have a degree 1 factor. So they're the nicest and most cuddly of all, because all I got to do really is plug in stuff and see if it's got a root or not. And neither one of these polynomials has a root mod 11. So in the Galois group, we have an element of form A, B, C, D. So there has to be an element in the Galois group that is the product of disjoint, a 2-cycle and a 3-cycle. Now, possibilities are those are the 5 transitive subgroups specified up to isomorphism. Now, what can you say about the order of a 2-cycle times a 3-cycle if they're disjoint? The order is 6, right? Because with disjoint cycles, the order is the least common multiple of the least cycles. So whatever the Galois group is, it's got an element of order 6. Bang, bang, bang. Order 5, order 10, order 20. And it can't be a 5 either. Why not? Yeah, this is odd, right? Because this is an odd cycle, so this is probably an even number of transpositions, so the whole shebang is odd, so it's not even that. So my poor little friend who should have taken the exam at the right time was in a little bit of trouble here. So. Okay, any questions on that?
Did it go well?
What's that?
Did it turn out well?
Well, it did for me, there was nothing to grade. It was pearl before swine, it was just blank, so, you know. And of course, I would have graded extremely sympathetically if he'd done anything, because I felt a little guilty about it. You know, I mean, didn't even do it. Okay, so let me give you one last theorem for today, and then I did promise you at the beginning of this section that I will give you an algorithm that will work for any polynomial over Q. I don't have time for that this time, we'll do that next time. But this is an answer to your Ben, your question about the roots, or it's not an answer, it's a partial sort of example. So theorem. Let P be a positive prime and f of x irreducible. So suppose you have a polynomial with integer coefficients, and suppose it's irreducible. So suppose you can write this, which ostensibly you can. If f of x has precisely 2 non-real oh, and of course this doesn't necessarily have to be over z, that's kind of the smallest case, but you can generalize this. If f of x has exactly 2 non-real complex roots, then the Galois group of f of x is the symmetric group on P squares. Let me briefly tell you why this is true. So it's irreducible, right? And so that means that the polynomial f of x of degree P is irreducible. That means the Galois group has an element in it of order P. Agreed?
And
Right.
positive B.
What's that?
And positive B.
Yes, did I not say that? I'm sorry. Thank you. Yes, it's an irreducible polynomial of degree 3. So, and of course, this is very interesting for P equals 3 to 5. So it's got degree 3 of P. So the Galois group has to have an element of order P in it, right? Now, in SP, the only elements of order P are the P cycles, right? Because to be of order P, your cycle, it has to be divisible by a cycle of P, and that's as long as you have. So you've got in there an element that looks like that. And because there's exactly two complex roots, you've got complex conjugation as an automorphism of this. And that complex conjugation only interposes two roots because the others are real, right? So you also have that. And once you have an end cycle and a transposition in this situation, then you generate the entire Galois group. This does depend very heavily on the fact that it's prime, but that's kind of a neat little result. So whenever you have a prime power polynomial or a prime degree polynomial, if you've got exactly two complex roots that are not real, it has to be the full SP. Any questions?
The second part is for every Sn or just for the SP with P prime?
Just because that's because the problem really is in the P cycle thing. Because, for example, even in S5, you have an element of order 6, like that, like this thing right here. And you need that full P cycle. And that's why prime is important. Okay. Other questions? All right. Well, we will see you on Wednesday.